All right, and welcome to another week of PreCal. So, what we're going to be introducing today are some new identities. So, these are called the sum and difference identities because we're adding or subtracting angles on the inside of sine, cosine, and tangent. If we were talking about secant, cosine, or cosecant and cotangent, we would just be doing the reciprocals of these. So, let's look at cosine. Notice that these are plus or minuses, and this is actually a minus plus. Well, if you're adding two angles inside of the cosine, you can take it apart into this, where you're doing cosine of the first angle, cosine of the other angle. You're actually going to do subtraction if you're starting off with adding, and then sine of each of those. So a good thing that we do to remember this is using CCOSS. We like to say COCOS sometimes. COCOS is trying to get you to remember that you're always doing cosine and cosine. You're always going to do the opposite sign of whatever it was. So if we're adding in here, we're subtracting out here. If we're subtracting in there, we're adding in there. So that's a good way to remember that. What about sine? Well, notice that that's plus or minus and that's a plus or minus. So this one actually has the same sign, but it's not sine, sine, cosine, cosine. It's actually sine, cosine, and then plus or minus cosine, sine. So what I like to do for this is just SCS, CS. So you're just, doing a pattern of all the letters starting off with sine because, it's sine and then cosine. And then this is the same sign and then cosine sine. So it alternates. So cos and SCSCS are kind of ways to remember these identities. Now, with tangent, there's not really a good way to memorize it, just besides, writing it over and over again and making sure you remember it. When we take apart tangent, notice that the top is pretty much taken apart, tangent A and tangent B, and doing the same sign. On the bottom, we're going to do one and then the opposite side sign of the two separated but multiplied. So write these out. This is a good way to memorize these, is to write them out. So how do we ask these types of questions? Well, let's find the exact value of this long equation. So what's cosine of pi over 16 on the unit circle? Well, pi over 16 is not on the unit circle, so we can't figure out that exact value. But what we could do is we can put this together using our new identity. So remember that if we're using cos, because it's cosine, cosine, and sine, so that has to condense to one cosine function. Well, what are we doing with these two angles? And notice that, we have pi over 16, a cosine and sine, and then a cosine and sine of the 3 pi over 16. So I'm going to put both of those inside of one cosine function. And cos is talking about the opposite side, sine. So instead of subtracting, we're going to add it. So we can actually condense this to one trig function of cosine by doing that. So then I do some basic math operations here where we're adding these two fractions together, and we get 4 pi over 16, which reduces to pi over 4. Is pi over 4 on the unit circle? Yes, it is. What is the cosine at that angle? Well, root 2 over 2. So we're able to take these long identities here and condense it to one. Again, using cos, where we're doing condensing it to one cosine because we start off with cosine and then we do the opposite sign. Usually if we start off with sine, if it's sine cosine, then we're condensing it to a sine. And of course, if it's tangent, that's only one way to condense it to tangent. So there'll be questions like that. Sometimes these condense into one, but it doesn't end up being on the unit circle, so you can just leave it like that. So find the exact value of cosine of 105. Well, 105 is not on the unit circle, but we do have a bunch of angles that are on the unit circle that we could figure out that add or subtract to 105. So you have to kind of think of two angles. Well, if you're wanting to start off with the smallest non-zero one, you would think 30. Okay, what would I add to 30 to get 105? Well, 75. Are those on the unit circle? Well, 30 is, but not 75. So that would not work. That would not help us out. We want to take it apart into two angles that add up to 105 that are on the unit circle. Well, 45 is usually one of the cases where it's always going to work out. So 45 plus 60 ends up being 105. So I could use that one. Well, what about some other angles? Well, we don't want to try to do 90. We want to kind of stick to 30, 45, or 60. What are some other angles we can do? Well, we can actually subtract. 135 is on the unit circle, and if I subtract 30 from that, hey, I get 105. So that could actually work. Well, then, like if you're thinking, oh, well, what about 120? Well, that would be minus 15, which is not on the unit circle. So you have to choose wisely. Again, you could figure out what adds to 105. You can figure out what subtracts to 105. Either one works. What I'm going to do is I'm going to stay simple and stick to the 45 plus 60. Why? Because both of those are going to have positive values and I don't have to worry about it. 135, you have to deal with the cosines being negative. So you have to be very careful with your signs. So taking apart 105 to 45 and 60, I can then take it apart into my cos, where I'm going to do cosine of 45 and then cosine of 60. And then it's the opposite sign of the sines of each one of those. So what's very important to understand about these sum and difference identities is that you should have sine and cosine of each of the angles. Sine and cosine of 45, sine and cosine of 60. You can't have cosine and cosine of 60 in the same problem here. Well, then we evaluate this more because, again, we're looking for the exact value. We want to have some radicals and stuff. So what's cosine of 45? Well, root 2 over 2. What's cosine of 60? Well, that's 1/2. And I'm multiplying those two together. Sine of 45 is root 2 over 2. Cosine of 60 is root 3 over 2. And again, we're multiplying those. Well, when multiplying fractions, we multiply the top times the top, the bottom times the bottom. When you have radicals like this, root 2 and root 3, you actually multiply their insides, their radicands. And then we can write it as one fraction since they have a common denominator. So this is typically what you will get as an answer when you're doing sine and cosine of an angle of two unit circle values that add up to that. Now, what happens if you would have went back and done cosine of 135 minus 30? Would you get the exact same answer? Yes, you would. The work might look a little different because you might have some negative signs going on there, but, and especially, well, if it's starting off with subtraction, you would be adding. But you get the same answer. Every sine and cosine will end up coming out to root 2 plus or minus root 6, and it could be plus or minus root 2 all over 4. So you kind of know the answer. You just need to be able to show the work and what you did to get there. All right, what about radians? So degrees are kind of easy. Radians, you have to kind of think a little bit more. Now, we could figure out what negative angles I could add up to get 7 pi over 12, or, I can subtract a small one minus the big angle and get a negative angle. But a good hint is to always get a positive coterminal angle. So coterminal angles is adding circles to this. So if I'm starting at negative 7 pi over 12 and I wanted to add a circle, well, circle's 2 pi, but if I want a common denominator, I'm adding 24 pi over 12. So we end up getting 17 pi over 12. You'll get the exact same answer if you try to figure out two angles that add or subtract to negative 7 pi over 12, or adding and subtracting a 17 pi over 12. Again, it's a little easier to think about two angles that add to 17 pi over 12. All right, so now it's the process of how do we get 17 pi over 12? Well, it'd be nice to have all these radians in terms of a denominator of 12. So let's start off with the smallest, so pi over 6. If I multiply the top and the bottom by 2, I get 12 pi, or 2 pi over 12. Pi over 4, I end up getting 3 pi over 12. And then pi over 3, I end up getting 4 pi over 12. Again, trying to get a denominator of 12. And so I'm multiplying by 2, by 3, and by 4, and multiplying the top and the bottom. These all reduce to those. Well, which one of these add up to 17 pi over 12? Well, none of them do. So let's move on to quadrant 2. So what about 2 pi over 3? Well, if I convert that to over 12, we end up getting 8 pi over 12. Can I add that with anything that can make 17 pi over 12? No. So let's move on to the next one. What about 3 pi over 4? Well, that's 9 pi over 12. Hey, wait a minute. What happens if I add 8 pi and 9 pi? you get 17 pi over 12. So let's use these two angles, 2 pi over 3 and 3 pi over 4, and adding those up. So I'm going to take this apart to tangent of 2 pi over 3 plus 3 pi over 4. And it doesn't matter what order you do this in. So are there other ways that you can get 17 pi over 12? Yes. You just have to kind of think about it and do some work with it. You have to try to make sure that you're getting all your fractions to be denominators 12. You can do subtracting, adding, whichever one that you find easiest. So let's take this apart. So if we're doing the sum identity for tangent, what we do is the numerator is just honestly them taken apart. So the tangent of 2 pi over 3 and then the tangent of 3 pi over 4, and then add them together because that's the same sign. The denominator is one opposite sign, and then you multiply those two together. So that is how we take apart and use the sum and difference identity for tangent. If this was subtraction, we would do subtraction down here and then adding on the bottom. So now we have to figure out what each of these values are. Well, tangent of 2 pi over 3 is negative root 3. Again, it's going to be helpful to know that any angle of 60, because pi over 3 is this reference angle 60, gives you root 3. Since it's 2 pi over 3, it's in quadrant 2, so it's negative root 3. Tangent of 3 pi over 4 ends up being negative 1. And in the bottom, we multiply those two. Okay. So again, knowing the unit circle is very, very, very important. So how can I simplify this? Well, I can end up saying negative root 3 minus 1 over 1 minus root 3, because those two negatives multiply to a positive. Now, we talked about radicals in the denominator and all that stuff in one of the other assignments, but we need to make sure that you understand that if you are doing this on an AP test, if you're doing it on the free response portion, then yes, this answer here could be right. However, it's probably not going to be in the multiple choice section. So how do I simplify this? Well, what we do is we multiply the top and the bottom by the conjugate that is of the denominator. The conjugate of the denominator is 1 plus root 3. And I do that to the top and the bottom. This is something that you should have done in Algebra 2 and Algebra 1. We definitely did it in GMAPS, where if I FOIL out the top, we end up getting negative root 3. And then we have negative root 3 times positive root 3, which ends up being negative root 9, or just negative 3. Negative 1 times negative 1 is negative 1, and then negative 1 times root 3. All over, some of y'all can see that this is a difference of two squares, but just to show all my work, for everybody to understand it, I'm going to FOIL out the bottom as well. And again, I get a negative root 3 times a positive root 3, so you're left with negative 3. So the top ends up simplifying to negative 4 minus 2 root 3, and the bottom ends up simplifying to negative 2. Well, all those outside numbers are divisible by negative 2, so you end up getting 2 plus root 3 as your final answer. So again, a lot of algebra that goes into it. I would strongly suggest, if you can, try to use pi over 3 or 60 inside of tangent, because it makes the problem a little easier because of it being root 3. If you do tangent of 30 or pi over 6, you get root 3 over 3. So you have to multiply everything by 3 to get rid of the denominators. So practice it. It is very helpful to know how it goes to. So like I said before, with all the sine and cosines of these sum and difference, you're going to have some kind of root 2, root 6 all over 4. Same thing happens with tangent. You should have 2 plus or minus, or positive and negative 2 and positive and negative 3, root 3. All right, what else could we do with this? Well, we could give you a trig function of one angle and tell you its ratio. We can do this trig function of a different angle and a different ratio, or it could be the same one, whatever. And then we're going to tell you a range where that angle is. Well, if x is somewhere between 0 and 90, that means my angle x is somewhere in quadrant 1. So I'm going to draw a triangle with an angle x here that's right to the horizontal. So that's my triangle. Doesn't have to look perfect, doesn't have to be to scale. If we're talking about sine of that angle, then we're talking about this being the opposite side being 4 and the hypotenuse being 5. So then our adjacent side ends up being 3 because it's a triple. Well, if y is between 90 and 180, that's in quadrant 2. So I'm going to draw quadrant 2. I'm going to draw my angle y. Doesn't have to have degree symbol or whatever. Or yeah, it doesn't really matter. I'm just drawing, a triangle with y. Doesn't have to be to scale. And then we have cosine is negative 5/13. Cosine is the adjacent side over the hypotenuse. And notice that I put the negative on the horizontal axis because the hypotenuse is never negative. It's always positive. We rarely use the word always. And then you should know the triple 5, 12, 13. And that's going up, so it's positive 12. So how do we use these sum and difference identities to do this? Well, if we're doing tangent of x plus y, kind of like what we talked about before, is I can take apart the tangent of x and y like that. Never does this end up equaling this, okay? Unless some weird situation happens. Like if they're both 0 or both some same angle. This should never equal this. Tangent of x plus y is tangent of x plus tangent of y over 1 minus tangent of x times tangent of y. That's the identity. This whole ugly fraction simplifies to this or vice versa. Okay, so make sure you understand that. Well, what is tangent of x? Well, what is tangent of our triangle with the angle x? What's opposite over adjacent, so 4/3. What about tangent of y? Well, it's negative 12/5 over 1 minus the product of those two ratios. Now, how do I simplify this? Well, I have certain things that I like to do with this just to make sure that it makes it easier, especially if you're doing this stuff without a calculator. What I want to do is I want to maybe change this plus a negative to just minus 12/5. And on the bottom, I'm going to multiply 4/3 and negative 12/5 and end up getting positive 48 over 15. And some of y'all are thinking, wait, that reduces. Yes, it does. However, to make the problem a little easier for yourself is if I don't reduce that, I can multiply everything by that denominator, and it ends up helping out a lot. So what happens if you multiply 4/3 by 15? Well, you end up getting 20. 12/5 times 15, you end up getting 36. 1 times 15, which is something that a lot of people forget to do, is you're multiplying everything by 15. 1 times 15 is 15, and then you get 48, which ends up simplifying to negative 16 over 63, which is fully simplified. This always happens. There might be a few cases along the way that you might end up needing to simplify again, but in most cases that I've seen, we do this and it ends up being a nice reduced fraction at the very end. So again, multiplying these, the numerators and denominators, and multiplying everything by the denominator makes the problem a lot easier to deal with. So how can I verify that this left-hand side equals 0? So remember that with all of our identity practice, we're trying to manipulate one side to look like the other. It's not really easy to make 0 look like that left side. So how could I use what I learned today to verify that this equals 0? Well, if you notice, they're both adding two angles inside of each of the trait functions. So for sine, we're going to use SES. So sine of the first angle times cosine of the second angle. The same sine and then cosine of the first times sine of the second. Then the other one is cosine of two angles that are being added together. So cosine of the first times cosine of the second. But it's cos, so we're going to do the opposite sign, so subtracting, and then we're going to do sine. But that's just kind of taking apart the sum identities, but what we're doing is we're subtracting these two. But if we're subtracting a binomial, we need to make sure that that binomial is in parentheses. So this is how that first step should look. And then if you kind of notice, like 7 pi over 6 and 2 pi over 3 are on the unit circle. Sine of 7 pi over 6 is negative a half. We don't know what cosine of x is, so we're going to leave it like that. Cosine of 7 pi over 6 is negative root 3 over 2. Sine of x again. And in this one, you might want to take up apart into 2 steps or just do it in one, where I'm subtracting or kind of distributing and doing the unit circle at the same time. So cosine of 2 pi over 3 is negative a half, but since I'm subtracting those two, they become positive. And then cosine of x. And then I'm going to distribute the negative, so that becomes plus. And then sine of 2 pi over 3 is root 3 over 2, and then sine of x. Well, then now we can combine some like terms. We have negative 1/2 cosine x and positive 1/2 cosine x, which is 0. Then we have negative root 3 over 2 sine of x and positive root 3 over 2 sine of x, which is also adds up to 0. So 0 equals 0. And that's our proof.